This lecture is going to go over the properties of waves problems, the handout that we started today in class. It is both classwork and homework. We'll start off looking at period and frequency. The period of a pendulum is the time it takes to move through one cycle. And a frequency is a term that refers to how many cycles can occur in 1 second. So you'll see that these are inversely related. For example, period measured in seconds is denoted by the symbol capital T. Period equals 1 over frequency. Frequency is measured in hertz. It's essentially like a per second. So the period is 1 over something per second, and the frequency measured in hertz, right, lowercase f, equals 1 over period. So these are inversely related. So if you have one, you can solve for the other. So let's solve a couple problems. So a string vibrates at a frequency of 20 hertz. What is its period? Well, period is 1 over f, so 1 over 20 equals 0.05 seconds. Notice, this is not the answer I'm looking for. This is. We're looking for a value here. It's measured in 0.05 seconds. And therefore, a speaker that vibrates with a frequency of 200 hertz has a period of, well, period equals 1 over frequency. 1 over 200 equals 0.005 seconds. So if a pendulum takes 10 seconds to swing through 2 complete cycles, how long does it take to complete 1 cycle? Well, it takes 10 seconds to go through 2 cycles. So it's going to be 5 seconds per 1 cycle. So how long does it take? Well, 5 seconds for 1 cycle. So what is its period? Well, 5 seconds. So what is the frequency then in hertz? Well, frequency is 1 over the period. So 1 over 5 seconds equals 0.2 hertz. Moving on to waves. A wave is a traveling oscillator that carries energy from one place to another. A high point of the wave is called a crest. The low point is the trough. The amplitude of the wave is half the distance from a crest to a trough. Notice, here's an amplitude, here's an amplitude, here's an amplitude, and here's an amplitude. And the distance from crest to crest or trough to trough or any starting point to another point is called one wavelength. So, and we'll identify a wavelength with the symbol lambda. So wavelengths can also be measured from trough to trough as well. So on the graph here, how many wavelengths are represented in the wave above in this picture? Well, there's 2 total wavelengths, so 2 wavelengths. So notice, here's one, here's the second. 2 total wavelengths. Well, what is the amplitude of the wave shown in centimeters? Well, let's see. Here's a 5, here's a -5. In other words, it oscillates back and forth from 5 centimeters here to -5 here. So it's a net displacement of 5 centimeters for an amplitude. So there's page 1. Page 2. So use the grids below. You're going to draw. You're going to label, make sure you're labeling the trough, the crest, etc. You're labeling parts. Well, I'm giving you information. What I want you to make sure you realize is that I need you to start to draw these to scale. So I'm going to give you a scaling factor of each square is going to be 0.25 centimeters. So that means a wave with an amplitude of 1 centimeter. Amplitude, right? How far from equilibrium? So that means if each one of these is 0.25 centimeters, right, based on the scale, 0.25, 0.5, 0.75, and 1. So 1 centimeter amplitude, well, that's the amplitude. The wavelength is 2 centimeters. So that means I'm going to need to go out 8 boxes to get to 2 centimeters. Remember, each square has a size, or in this case, a scale of 0.25 centimeters. So what I can do here is I know that 4 out is half of a wavelength, and 8 out is 1 full wavelength. And so here you'll see that I drew 2 full wavelengths, and we need some practice with this. In this case, the wave with an amplitude of 1 centimeter is drawn in red with the wavelength of 2 centimeters. In a different color, I drew in black, is a second wave that's 180 degrees out of phase of the first one. So wave A takes 4 seconds to complete 1 cycle. Well, what is its period? Well, if it takes 4 seconds to complete 1 cycle, its period is 4 seconds. And the frequency is going to be 1 over 4, which is 0.25 hertz. Moving on to the next problem. If I look here we go. A wave has an amplitude of 1.5 centimeters and a wavelength of 3 centimeters. Well, here I'm having you label each box is going to be 0.5 centimeters. So the first wave, 1.5 centimeters, that means I'm going to need to go up 1, 2, 3 boxes to draw my first wave. And notice, if it's 3 centimeter wavelength, I need to draw it, I need to count out 1, 2, 3, 4, 5, 6 boxes. Then I just connect the lines, connect the points with what I know this graph looks like. And I drew 2 total wavelengths. And I kind of botched it right there. Not a big deal, right? You can make some mistakes here. But this is what it looks like. This is what the first wave looks like. The second wave, a wave with an amplitude of 2.5 centimeters and a wavelength of 6 centimeters, is going to look different than the first one. Notice, larger amplitude, larger wavelength. So when I draw this, I've got each box is 0.5 centimeters. So 0.5, 1, 1.5, 2. I had to actually extend this to make this fully fit. And I just connect the points and draw it out. So the rules kind of help make sense of as to how I draw it. Right? I need to make sure I follow my scale. So wave B takes 0.5 seconds to complete one cycle. What is the period? Well, the period, 0.5 seconds. And the frequency, well, 1 over 0.5, it's a frequency of 2 hertz. Moving on, let's solve the problems at the bottom of this page. A water wave has a frequency of 2 hertz and a wavelength of 10 meters. What is its speed? Well, speed, here's a new equation we need you to write down. Speed is frequency times wavelength. 2 hertz times 5 meters equals 10 meters per second. Number 4, a wave has a speed of 50 meters per second and a frequency of 10 hertz. Calculate its wavelength. Well, now I'm isolating wavelength. That's my lambda. So lambda, right here, is going to equal velocity divided by frequency. So 50 meters per second in the problem divided by 10 hertz. So 50 divided by 10 is 5. My wavelength is 5 meters. Number 5, a wave has a speed of 30 meters per second and a wavelength of 3 meters. What is its frequency? Well, frequency is going to equal to speed divided by wavelength. So 30 meters per second divided by 3 meters is 10 hertz. So I'm really using this 3-variable algebra equation to solve. And I need you to write this down. Speed equals frequency times wavelength. And really, these other two are just isolating the other variables. So recall that a frequency of a wave is 1 over period. And the period of the wave equals 1 over frequency. So if a wave has a period of 2 seconds and a wavelength of 4 meters, calculate its frequency. Well, the frequency is going to equal 1 over t. So 1 over 2 seconds has a frequency, right? Frequency is 1 over t, period of 2 seconds is 0.5 hertz. Therefore, the second part of this is that it says calculate the frequency. Well, it's 0.5 hertz. And the speed is going to be frequency times wavelength. 0.5 hertz times 4 meters, right? It tells you a wavelength of 4 meters is 2 meters per second. The wave speed here is 2 meters per second. And a sound wave travels at 330 meters per second, has a wavelength of 2 meters. Calculate its frequency and period. So frequency is going to equal wave speed divided by wavelength. So 330 meters per second divided by 2 meters is 165 hertz. The period equals 1 over frequency, right? 1 over 165 is going to be 0.006 seconds for the period. Now, as we carry on here, I've done this so that I can just kind of highlight it. I want to make sure you realize amplitude is the distance from equilibrium to the highest and lowest points, right, to the crest, to the trough. We should be labeling those wavelengths here. Notice wavelength is where a wave starts and goes through a full cycle. This has 2 full wavelengths here. Drawing them in phase and out of phase, I think you need to make sure that you draw and label the one cycle here at the top. I've broken down into 360-degree increments. Halfway is 180, half of that is 90, and even half of that's 45. So I've tried to draw these. I don't want it to look too busy, but I drew the 45 degree in black. I drew the 90 degree in blue. I drew the 180 degrees in red. And I can essentially just, you can pause this and make sure you're able to take a look and make sense of this. I expect us to be able to graph. For creating a graph to scale, it says draw 2 waves total. The wave has an amplitude of 4 centimeters. We're using the scale of each box equals 1 centimeter. So if I look here, the amplitude of 4 centimeters should be 4 boxes. So 1, 2, 3, 4. Has a wavelength of 9 centimeters. So if I count 9 out, that means 4.5 centimeters is my midpoint. And in a different phase, I said we'll draw one out that's 180 degrees out of phase. So that was drawn in red. If it takes 4 seconds to complete one cycle, right, the period's 4 seconds, the frequency is 0.25 hertz. If you label the crest and the trough here, it says calculate period and frequency. It's kind of the same thing. I kind of did it twice here. Look here at part 3, understanding what's taking place within the graph. If you draw a sketch here, there was already one drawn. I asked you to draw 180 degrees out of phase. I drew that one in blue. Right, it's at opposite locations from the example that's in the picture. And the 270 degrees out of phase I drew in red. That is just at a different location, a different phase than the picture, than the drawing that's in black, labeled A, B, C, D, E, F, and G. So how many wavelengths are in the picture? Well, if you look here, it should be 1.5. There's 1, and there's the half, 1.5. So if each wavelength is 4 meters, what is the distance of A to G? Well, you know that one wavelength from A to E is one wavelength of 4 meters. The E to G is a half wavelength. That's going to be 2 meters. So 4 plus 2 tells me it must be a total of 6 meters from A to G. So how many wavelengths are shown in the picture? Well, 1.5. So what combinations represent a half a wavelength? Well, there's a lot of ways. You can say A to C, B to D, C to E, D to F, and E to G. Those are the letters within here, combinations. So if the total distance A to G is 24 meters, and the time is 48 seconds to go from here to here, what's the size of one wavelength? Well, that's 16 meters. And what is the wave speed? Well, speed is going to be 16 meters divided by 32 seconds, or 0.5 meters per second. So here I'm looking at part 4, period and frequency. An oscillator completes 60 cycles in a minute. What's its frequency? Well, I know that 60 cycles in 60 seconds is 1 hertz, so the answer is 1 hertz, right? You need to know how many seconds are in a minute. A wave on a shore arrives every 4 seconds. Its period is 4 seconds, and its frequency is 0.25 hertz. Which picture below has a greater frequency, and how do you know? Well, this is going to have a greater frequency. There's more oscillations per unit of time. And here, it says lower frequency. There are fewer oscillations in a unit of time. Part 5, moving on to the last page. The labels, you should be able to label these. That's kind of just a revisitation of it. When you graph this, the total distance on the graph is 12 meters. What's the size of one wavelength? Well, notice that there's 2 total wavelengths here. So if it's a total of 12, half of it would be 1 wavelength. That would be 6 meters. If it takes 6 seconds to complete one full oscillation, right? So 6 seconds here. So the wave speed is going to be 6 meters divided by 6 seconds, which is going to be 1 meter per second for a wave speed. Part 6 has you creating a graph to scale, and you can pause this. It's harder for me to go over every single part here for the graphing piece, but you're going to need to know how to do this. It's good practice. And each box represents 2 centimeters, so you'll draw 1.5 wavelengths total. It has an amplitude of 8 centimeters, has a wavelength of 24 centimeters. Draw a second wave that's 90 degrees out of phase, and I did that in black. So, there's a lot going on. You can always pause this and take a look at it. If wave A takes 10 seconds to complete one cycle, calculate the period and the frequency. Well, if the time is 10 seconds, that's the period of 10 seconds. And the frequency is going to be 1 over period, so 1 over 10 is 0.1 hertz. In crest, trough, wavelength, period, these are you should be able to label those in here. I'm going to move on. I'm running out of time. I only have 15 total minutes, and I'm at 13, so I've got a couple more to do. So understanding what's taking place here, when I look at this, draw a simple sketch here, and you can label on here. How many wavelengths are shown? There should be 3 total wavelengths. Here I have 1. Here I have 2. Here I have a third. So if the distance from A to F is 12 meters, A to F, here it is, 12 meters. What's the size of one wavelength? Well, that means I know that here's half A to F is halfway, so that means 12 meters there. 12 meters from F to G, that's 24 total. If I have 24 total meters and I have 3 wavelengths, I take 24 divided by 3 and I get 8 meters. So the size of one wavelength is 8 meters. What's the distance from A to G? Well, A to G here would be 8, 16, 24, so it would be 24 meters. If it takes 5 seconds to complete one oscillation, what is the time represented on the graph? Well, 5 for 1, 10, so 5 more, 15, should be 15 seconds. What is the wave speed? Well, the distance of 8 meters divided by 5 seconds, right? The distance of 8 meters, time of 5 seconds, is 1.6 meters per second. So which letter combinations represent a fourth of a wavelength, and which 2 letter combinations are 1 full wavelength? You can answer you can take a look here. Oops. Here I answer it in half a wavelength. Here I have it written as a fourth. My bad on that. I'm answering it, I believe, A to D is a half of a wavelength, and so is D to E. So change that to 1/2. I'm just catching it now. Total distance from A to G is 36 meters, so I'm giving you a different scenario, 36 meters. The time on the graph is 36 seconds, so the time to complete this is 36 seconds. What's the size of one wavelength? That would be 12 meters. Notice it's based on this picture. It's 1/3 of the 36 meters. And the wave speed would be 12 meters divided by 12 seconds of 1 meter per second. All right, last one. I'm not going to be able to get it all done, but you can pause this and take a look at it, and that should help you with the first part of your homework.